What's up, YouTube? In today's video, I'd like to talk to you about scaling RDBMS databases. Truth be told, this talk started off as a simple sharding example or an explanation for sharding, which then drove me into digging more in or thinking that I should sort of explain the hashing aspect a little bit more. And then finally I said, well, then if I'm talking about sharding, maybe I should be explaining to you why or when you should be thinking of scaling your databases. And then that blew up into this whole conversation here. So I hope you find this interesting. As is usual, I like to build a foundation understanding rather than just give you like a solution. So this video might turn out a little longer than you would imagine, but I think it's important, which is why I spend the time thinking about this stuff and making a video for it. So here goes. Scaling a database is one aspect. Knowing when to scale is another aspect. Knowing what kind of scaling method you should be using is, of course, the third aspect. So we're going to start with what I think is more important, which is even before you think you need to scale your database. It's like a checklist of things you need to look at before you even go down that path. Then we're going to be discussing the different ways in which you can potentially scale your database, and then mainly focusing on sharding, which was the original sort of genesis or germ for this talk in the first place. And while we talk about sharding, I'm going to talk about hashing and hash functions, just enough to get you to understand what hashing is all about, and then therefore how sharding works. Okay, so without further ado, let's get started. So as you can see here, before we can even think about scaling, I want you to start to think about, well, this is not that. This is just a basic, you can look at the slide and pause, but essentially I'm trying to say that this is also something that some people think. Let me know if you think this way or if you've heard people thinking this way. RDBMSs cannot scale. They can only scale vertically. And the only way to scale is to go to like a NoSQL store, right? If you've heard that, then this slide is for you. If you think that, this slide is for you. If you heard this, you could probably show this to the people you heard it from. I've worked certainly on RDBMSs way many more years than with NoSQL stores. I was first introduced to a NoSQL store in 2007 when Azure, towards the end of 2007 when Azure first came out. It was a mind-bending exercise. I finally got it. There was no documentation to help out, to help you understand how to use these databases. I was migrating billions, that's with a B, billions of data records, 40, 50 billion records to Azure. And it just wasn't something that, one would imagine would work in a commodity hardware thing like, and at the time it was Azure Table Storage. To cut a long story short, there's nothing wrong with NoSQL stores. There's nothing wrong with RDBMSs. To think that one is a substitute for the other is incorrect. To think that one cannot scale while the other can is incorrect. Yes, there are certain challenges with trying to scale RDBMSs horizontally, but today's topic is exactly that. Both solutions are horizontal scaling. To a certain extent, that just works. There are many, many companies, large companies today that are still using RDBMSs like Stack Overflow, YouTube. YouTube started its life before Google bought it on a RDBMS. They finally had to employ one of the techniques we're going to talk about today, sharding, as part of their way to be able to grow just before Google bought them. Today, they're still on that RDBMS with the sharding. So if Google can do it, you can do it. Or if YouTube can do it, you can do it. I think a lot of us kind of, imagine being these, the stars. And so we want to do what the stars do. And if we do what the stars do, then we'll become the stars, right? Well, today's talk is about what you should be doing before you think about scaling, because there are many, many things that you should be doing before you even think about scaling, because there are many things you've not got right yet. And it's only when you've exhausted all of those options should you be thinking about scaling. So I won't dwell on this slide, but let's move on to the next one. All right, this slide is before you think about scaling, right? And this one is focused more on the database and stored procedures, query plans, hardware, logical model, physical model, that sort of thing. All right. So there's a bunch of things you want to be watching out for. So have you done the analysis on your query plans and your indices? Then there are many, many tools in SQL Server today, just out of the box, that can help you with the query optimizer, the index optimizer. You can analyze and optimize your queries, your indices, and all that. Now, don't follow these tools blindly. Understand what they're saying. Make sure you understand if what they're saying is correct. And obviously, when there are too many indices, that can actually slow you down quite a bit as well. So too many indices could make your writes and updates slower. Maybe the reads improve. And do nothing without just blindly following the advice from these tools. Make sure you have benchmarks in place and you look at each of the options and see if you're actually improving or degrading your performance based on the suggestions that you're adhering to from these tools. They're solid tools, but don't just follow them blindly. Make sure you have a baseline before you start with anything. All right. You have to know, right? I mean, at the end of the day, if you're spending time and effort behind something, you have to know if you're improving, if you're going in a positive direction or a negative direction. So the logical and physical data model. This is key. See, in one of my videos earlier from many years ago, I talked about how it is important to, if you're trying to be a driver, like a programmer driver, that similarity. But if you want to be a better driver, you have to understand the car you're driving. You have to understand the engine of the car you're driving. You have to understand the road you're traveling on. The better you understand your engine, the better you understand the road you're traveling on, the better driver you're going to be, right? The same thing applies for databases. Just knowing how to write really cool SQL doesn't make you a good DBA or a good programmer who understands databases. You have to understand the hardware. You have to understand how the database engine utilizes this hardware. When you look at a query plan, the query plan might suggest, that's not doing a table scan, that's actually doing a hash join. Perfect. So at least it's using the indices. Great. But knowing that it's doing a hash join, are those tables in the right physical hard drives? If these, let's say you got these 3 queries or 4 queries that are the most common queries, and if these 4 common queries are constantly utilizing large tables to do joins and such, should these tables be on physically separate hard drives? What about the hard drives themselves? Should they not be SSDs or a RAID array? I've had a situation where I've migrated a database where every drive letter was a RAID array of 16 drives. It was some of them were RAID 1.0, some of them were RAID 6s, but nonetheless, each drive was comprised of more than one drive. And that time, SSDs were quite expensive, so we didn't go down the route of SSDs. We had SSDs for some drives that, like TempDB and such, that were, and it probably was the wrong choice at the time because the SSDs weren't the best suited for that kind of rewrite pattern. So we later switched them out to be another RAID array. But the idea is that there's a logical model, data model, and there's a physical. You have to understand the difference between these two. You have to understand how best to design the physical database, not just the logical database. Of course, you want to look at the logical database and make sure it's correct as well. These are all things you're looking at in your database, in your data model, in the physical and the logical, before you think of scaling. So let's back up a little bit. You're thinking about scaling. Why? Hopefully it's not because you're doing what I call resume-driven design, right? We've done that before. Okay. I see this resume-driven design happening a lot. There's a lot of devs who are suggesting use of certain technology and certain techniques just because they can potentially put it on the resume. Sure, you want to gain the experience, but then that experience means you can now put it on your resume. So let's assume it's not that. You have excessive amounts of load or excessive amount of queries, too much data. Something is saying, hey, I need to see how I can scale out this database. Right? That's really the driver. So that means you are already in trouble in the sense that you're feeling the pain. You're starting to feel the pain and you're hopefully looking ahead, figuring out like, how am I going to take this system like to that next level? Next year we're going to have 100,000 more customers and now we go able to handle the load given our current situation, right? So look at these things, right? The hardware. Databases are extremely dependent on hardware. I can't tell you how much dependent they are. They are completely dependent on the hardware. It's like you have to feed them the hardware so that they can give you back the data. If you had let's say you had a budget to buy a hardware database server, right? Let's say $1,000 budget, and you have to portion out the budget on 3 different kinds of things: hard drives, the space as well as speed, RAM, memory, and CPU, number of cores. What portion of this budget, $1,000 budget, would you proportion towards hard drives versus memory versus CPU? Think about that. Okay, hard drives are the slowest. Hard drives are about 1,000 times slower than RAM. RAM is about 1,000 times slower than CPU. CPU is the thing that's doing the work. If the CPU doesn't have the data to operate on, it can't do the work. It's sitting there twiddling its thumbs, which means the RAM has to feed it the data. But the RAM is dependent on the hard drives to get the data into RAM. So the data is not coming fast enough into RAM. RAM can't give the data fast enough to the CPU. So the CPU is spending all of its time sitting around twiddling its thumbs. So you get it right. Hard drives become the key. They're so much slower than CPU cores that buying more core. I mean, I'm not saying you should go to like a 2-core machine. Multiple cores helps the machine do multiple things simultaneously. But what I'm saying is that those cores could be potentially starving, and they're not saturating the cores with all the processing they need to do. So the idea is to saturate the cores. If your cores are not being saturated on the biggest workloads, there is something wrong. It's not getting the data fast enough to be able to saturate the cores. It is a little backwards from, in my experience, I know most people think that saturating all cores is a bad thing. I'm saying when it's supposed to be saturated, it bloody well be saturated. Right? So just because the cores are saturated doesn't mean it's a good thing or a bad thing. Was that the intent? If I expect this thing to be going at blazing speed, full speed ahead, it should be pegging all cores at 100%. If it's not, I'm wondering why not? Is it not getting the data fast enough to be able to saturate all cores? Right? So that's where you have to look at. So if I know this operation is supposed to tax the system such that all cores are saturated, and they're not being saturated, now I have to think about why not. If it is, that's great. Conversely, if the cores are being saturated for something I don't expect, I need to dig in to figure out why is that? I don't expect this operation to saturate all cores. I mean, of course, the duration also probably matters. So these are things to consider in a database. It's a very hardware dependent thing. You have to understand how it uses the hardware. All right. So then over the years, database engines have had some new features added to them. One of them, SQL Server introduced, I think, way back in 2008 or maybe even earlier, actually. Yeah, actually it was earlier. 2005, maybe? Indexed views. In Oracle, they call them materialized views, I think. Index views is a great idea, right? Because you got to be careful. You have to understand. See, try nothing without doing like a benchmark. An index view is essentially a join, or like however you would normally do the join in your queries. Rather than having to perform that join each time you run the query, the join is pre-performed and it is persisted to hard drive. So there's actually a table now on your hard drive that is the join equivalent of those tables, and the database engine manages that table, the physical table. So it's actually saved to hard drive, and each time any updates occur in any of the dependent tables, maybe there's 3-4 tables that are joining in, the database engine manages the updating of the view, which is the persisted view. So the next time you fire the query, it's not trying to do the join, it's already done the join. You can just pull this up, from your hard drive. Of course, that implies you got some super, speed hard drive so that it can actually do that and may benefit from it. If your hard drives themselves are bottlenecks, well, it's not going too much faster. Certainly be beneficial, but not too much faster. So there are some constraints on index views, so you might want to look at that before you just jump in that direction. But it's a great alternative to try and speed up some queries if that's what your issue is. And remember the physical data model as well that needs to be played with and worked around based on the queries you're firing. Okay, indices with included columns. Another concept, another feature in SQL Server that was introduced maybe in 2008 timeframe or maybe later was the notion that not only can you define indices, which is pretty common for most databases, indices with included columns. The short of it is that when you define an index, let's say on let's say username on a database, then that username is in the index table, and then there's pointers, if you will, to the original record, the table and the record on that table, with regards to sort of jump to that record to get the rest of the data. Let's say you want to know the first name, the last name, the email address, all those kind of information. If your queries are constantly using additional columns, then you could include those columns in your index as well, index table. They're not being indexed on that, but they're there. They're physically present. The values are. And the database engine will again do the synchronization of data. If it changes in the main table, it'll change it in the index table. The idea is when you're doing that query, then it doesn't have to jump from every record in the index that it found back to the main table. It simply gets all the data it needs from the index table and speeds up your response times. So you might want to think about that. So there are a lot of things that are available in database engines today that most people don't understand, don't know, don't exist. And then they're happy to blame the database engine as being the culprit. Right? So you have to think about, I don't know enough. And I can tell you this is more often than not, I don't know enough. Right? It's very rarely that I know better than whatever is going on there. And so I can already jump to some sort of a conclusion. So I think rather than blaming the database engine or whatever it is, because, our lack of understanding, I'm saying, understand that database, understand whatever it is, the technology, the technique, the language, the platform, whatever it is you're working on. It is never at fault. You are at fault most times. You need to think about what, have you missed that it can do that you're not utilizing or that you don't know about, or how best you can use something to your advantage, right? It's about learning how to use these things. It's not so much about throwing away this thing to go for the next one. So before you make that jump or think you need to make the jump to either scale out or to like a NoSQL store, think again. There are skill sets, there are experiences that you're throwing away that you don't understand that you have and your team has or the organization has that could have a much larger impact if you were to make some major changes. And there is no free lunch, which means nothing you do to try and get out of this mess is going to come for free. It may seem like it's going to solve your problem, and maybe it does, but those solutions come with many more problems, different problems, right? There is no free lunch. There's nothing that gives you a solution just by itself. There are many caveats to these solutions. There are many unknowns, many new learnings that have to occur, different kinds of other problems. So you didn't get these problems, but you have those problems. Okay, so, and of course, as I said, I talked about the hard drives. You need to think about hard drives, even if it's just SSDs over spindle hard drives. Maybe it's RAID arrays if you're, depending on how much data you have. Big data. A lot of people see NoSQL stores are good for like big data for the most part. And this has been mainly for analysis. So YouTube and Stack Overflow might be using a NoSQL store today. I know Stack Overflow many, many years did not, until date, does not use any NoSQL store for its main operations. And so does YouTube. But maybe for reporting analytics purposes, they may use a NoSQL store. Right? Because that's a different kind of purpose. In fact, that's like what we would do in the back in the day. We would have a data warehouse database and an OLTP database to kind of satisfy these two different needs. So I'm talking about like from the day-to-day, the OLTP purpose. So you need to think about that database or the data model and the hardware requirements for that database. All right. Now let's look at the C# side of things. There are many things in the C# side that you should be looking at. Number one, are you using EF? Listen, if you're using Entity Framework and then you're complaining about performance, I'm sorry, but that's like an oxymoron, right? It doesn't make sense. How can you say, it's like, okay, you're in first gear in a car, right? The car itself is like from the 1950s, let's say. Think, damn, this car is not going, really fast. Like, what do you expect? First of all, you're stuck in first gear. Like, do you not know there's like a third and fourth gear? And second, you're driving a car that was like from, way in the back technology. So you can't blame. I'm not saying EF is old. What I'm saying is EF was not built for performance. They're certainly trying to make it as fast as possible, but it was not built for that. EF is built on top of AD.NET. You want to use AD.NET or Dapper to get the performance. And these are not hard tools, okay? One of the other things I found, and you can tell me if you think this is the case with you as well. People who are happy to blame the tool, don't understand the tool. Right? If you're happy to move from SQL Server to a NoSQL store, it's because you don't understand SQL. So you don't understand NoSQL stores either, but you're scared of RDBMS. You don't understand the SQL. It's too enterprisey, right? It's like one of those scary things that you don't know or understand enough of. Just embrace this stuff. You'll be all the better for it. RDBMSs are here to stay. They are not going away anywhere. And there's very few companies that need to get off of RDBMSs. Very few companies that need to be on a NoSQL store for everything, right? I've done that only because back in the day, cloud did not have the option to go to a large SQL Server database. I think the largest database that Azure offered at the time was like a 1 gig database, SQL Server database. So the only option you had was to just switch over to Azure Table Storage. Well, I'm all the better for it today, but I also understand the pros and the cons, and I'm certainly not at the same level of expertise with the NoSQL stores as I am with an RDBMS. And that's the other thing, you have to understand your limitations. I mean, listen, if you haven't had a NoSQL store experience, you're not going to suddenly become an expert overnight. I mean, I've been doing this for, I said 2007, so I've been doing this for like 13 years. And I still don't feel that comfortable the way I feel with SQL with RDBMSs. Some of it is, of course, that in the 13 years, I've not had a huge, it's not like every system I built was a NoSQL store-based system. So in the 13 years, let's say I've, had 8-9 years of experience with NoSQL stores. But even then, it's not, you don't become an expert because you had, 8-9 years of experience. I certainly don't feel comfortable yet. But I feel I'm in this place where I can very easily contrast the, between NoSQL and SQL data stores and immediately know that whether this is a NoSQL option or not, or a SQL option or not. Anyways, digressing into the NoSQL world, maybe I'll make a talk on that. But back to the C# things you can do in C#, right? So use AD.NET. And by just using AD.NET, I don't mean just switch over to AD.NET. No, you have to understand the best practices with AD.NET as well. If you've never done that before, you need to understand that. There are lots of ways in which you write your code that make the difference to the performance of your system. And I'll talk about some of those here. All right. This next one is interesting. It seems like way out of the world, but or some cases, they'll say, of course, but they don't realize they've not been doing this, right? And conversely, there's people who truly understand what I'm saying and they're saying, oh, that's not possible. So it goes both ways. For every request that comes into my system, I only allow one database call. That's it. You cannot make more than one database call. Now I can adhere to this principle maybe 99% of the time. But it's something you have to strive to aim to do, right? And then you hit the 95% mark. If you don't strive to do it, it's not going to happen. The idea is that the IO-bound IO network calls are the things that slow you down, right? So if you're going to be doing something that slows you down more often, then that doesn't make sense. You might make one trip to your database, get back all the data, or with one trip, send the database all the data it needs, and come back with the data that you need for the response, right? So make that as a goal. One request coming into your system, one database call. I can do that about 99% of the time. So there may be the one or two cases that you can't do that, even if you could, it's more like this, the tipping point where the effort is way more than the gain. And so it makes sense to just make two calls. What about responses? As in, for every page, you need to get a certain amount of data to fill up these pages. And this page is comprised of like different portions, right? Unfortunately, the Vue.js's and the Angulars of the world force you down a path that I don't agree with. And that is one request from the browser to your backend system for all the data required to populate all this stuff, right? In fact, I'll go one step further and saying by the time you rendered the page, the loaded page should already have the data in it. You don't have to make that trip back. As you store the data in some form of a JSON structure that on load time, the JavaScript will populate the page, but you never have to make the additional tip for the data. You don't have to make tips for the CSS and the images and all that. But even that, of course, there's lots of ways to optimize that. But what I'm saying is make as few trips back from the browser to your server as possible. This idea that for every little piece of your website, the parts of your page, that you have to go make JSON calls back to or AJAX calls back to your server is totally wrong, right? You need to satisfy the entire view with one request, one call to the database, and back out. And it's multiple result sets, by the way. So it's not like one query; it's multiple result sets. If you haven't worked with multiple result sets, then you need to learn how to do that. With AD.NET, it's pretty simple, right? It's you get multiple result sets back in your query, and you just say next result set, and you're populating, whatever data you want. Each result set is a completely different schema, and so with one query, you can get all the data required to fill up and populate that one page, right? So it's a different style of thinking. I've done it all the time, so for me, it's not unusual. But I've never had performance issues either, and I've had scaling needs to scale, except for the one case, where once you're in Azure or cloud, because the cloud itself had some limitations, but they could not give you larger machines to kind of scale your RDBMS. Today, they're huge machines. I mean, today the machines are, what does Microsoft call it? Beast. They call it, so these machines are called Beast. Internally, this is internal to Microsoft. They call them the Beast. And then they have the son of a beast, so on and so forth. Now there's a beast 2 and so on. These are massive machines. These are, 400, 300 and something cores and terabytes of RAM. And so they can offer you machines like that today, but back in the day, you didn't have that option. And I'm not saying you want to go down that route, but I'm just saying when the need arises, you can actually use very hefty machines. You can scale out with RDBMSs like I'm going to show you today, but you can also scale up and out if that's what you need. All right, so we talked about all the requests. Now let's look at table value parameters. This is such a unfortunately hidden gem in .NET, in AD.NET. It's not available in EF, and so I think nobody knows it even exists. And when I say table value parameters, people think I'm talking about table valued functions, and they're not the same thing. They're two totally different features. Table valued parameters allow you to essentially send a table as a parameter to your store procedure. This table is got like a schema, if you will, right? It has certain columns and the column data types and the number of records. You can send that from C# in a single request over to database, and you can have multiple store procedure parameters that are table valued parameters. Essentially, you can send multiple tables to your store procs at the time of making the call to your store procedure. Now, these are tables in your store procedure, meaning they look like tables. So you can do joins and a bunch of other things, just like you can do with any other table that's sort of part of your database. An extremely powerful feature allows you to make updates, large numbers of updates in one call to your database, right? So one network call, and you can make inserts like header details and whatever, many features like that. So think of it as, tables going across the wire. And you can stream these tables into your database, just like you can stream data out of your database using the data reader, which is like one of the next points here. Yeah. Right. So think about that. If you haven't used table value parameters, it's time to look at using them, because it totally speeds up your workload, especially when you're dealing with multiple results or multiple records to be sent across to your database. Make one call instead of multiple calls. Okay, we talked about the returning multiple result sets per database query. What about data reader? Data reader is a super fast forward-only, read-only cursor. Right? It's super fast. It also supports streaming. If you don't know what streaming is, I've got 2 videos on streaming. One is, I'll put a link to them here. One is streaming just generally in C#. The other one is streaming using the C#8 streaming feature. You can combine the data reader along with the C#8 feature to get that double streaming or proper streaming, if you will. And that'll speed up things as well, right? All right, so I think that these are the top level things at the hardware, database, store procedure level, and then in the C# level. If you've done all these things and you still feel like not going to pull it off, which is possible, right? I mean, you could be doing everything right, and you've actually hit a limit, if you will, at the hardware level where you are required to scale your database. All right. That's when you want to move forward. Of course, some of the exercise here is just to teach you some of the things, like the different ways you can scale and what. So, they shouldn't stop you from watching the rest of the video in case you don't feel like scaling. You at least learn about it. So there are two forms in which we can scale. So one is the read replicas or read scale out, which we'll talk about first. But the meat of the talk here is about the sharding or horizontal partitioning, right? So what's the read replicas? The basic idea is this. Let me just flip my pen here. That's your application making a call on a database. Let's assume this is not there for now. You just have this one. And this is the database that's sort of feeling the pain. You say, man, if I could just scale this database out. So the idea with read replicas is, and this is a feature of SQL Server, as in you have to set it up, but it's not like you have to manage this data yourself, but you can let SQL Server know you want to use these read replicas. It'll make one of them your primary read-write replicas and then the other secondary read replicas. It's managed by SQL Server, right? It's something you have to do. You have to set it up, but you don't have to manage it. The idea is that every time you do an update or an insert, it happens to this physical machine. Think of these as identical database. If the schema and the data and everything is identical, the hardware potentially also is identical. These are physically different machines. And you're writing to this one server here, but as you write and update stuff here, it replicates that update to the multiple read replicas, allowing you to then use these machines for queries, for reads, while you use this machine mainly for writes and updates. Right? So that's the point of this. So the idea here is you would use this scale out mechanism when you have too much load. Right? When you have too much load, the pressure, like too many queries coming in at you, and you're feeling the pressure and it's not able to keep up. At that time, you say, okay, well, what if I had multiple machines where I could direct, different requests to these different other machines that were doing only the reads, they're not doing the updates. And it's a very valid option because, of course, with reads, you just read, you're not writing, you're not blocking, locking, right, in that sense. And so when there's too much load, this makes total sense. By too much load, I mean the load in terms of queries is too much. It's not like you have too much data. You just have too many queries going on. And you can dedicate the reads to these machines and the writes here. Now, one of the issues with this model is that when you make a write here, it takes a few milliseconds to replicate to all these nodes. There could be like a delay, between the write happening here and the data appearing on these nodes, right? Or if any of the nodes goes down, then there could be a delay before that write happens to that node. It has to wait for the node to come back up and then so on. So that's all managed by SQL Server, but that's one of the drawbacks, right? So as I mentioned over here, again, this is pretty common. Most databases, we have more reads than we have writes. It's like almost 80-20, where 80% of the operations on a database are reads, 20% of the time it's like a write. So if that's the case with your database, then this makes a lot of sense. We have read replicas to help you with the 80% of the reading part, right? The write speeds remain the same, of course, because they're being written, you're still writing to this one machine. And the data is eventually consistent, meaning it could take potentially, milliseconds, half a millisecond to a second or so just to get replicated. But that's something that you have to be considering. Now, if in certain cases that eventual consistency is not an option, then you can read back from the same primary, right? So you write to this primary here and you read it back from here. It's already got the data here. You don't have to wait for it to replicate. But in most of the cases, you would just be going to these machines rather than hitting this machine here, right? So that's the read replica option for scaling out. I've had situations where one of these secondary read replicas had better hardware just because we were using this one machine for some reports that were just very, very taxing. And rather than beef up all the machines to the same hardware, only one of them was beefed up quite a bit because we'd use that one specifically to run those reports, while the others were helping us with the day-to-day kinds of queries for our online systems, if you will, right? So that's also possible. It doesn't have to be the same hardware, but it's all managed by the SQL Server. The schema is the same, right? But the hardware doesn't have to be the same. All right. the next option. Sharding or horizontal partitioning. You do this when you have too much data. Right? So you're scaling out horizontally. Scale out means horizontally. You don't have to say scaling out horizontally. But I'm sort of making a point. Scale out means horizontal. Scale up means vertical. So you're scaling out and you're trying to distribute the workload with regards to the data, amount of data that you have to manage. Right? So this is when you have too much data. So you're scaling out. So I'm going to paint a few scenarios. Remember, this is the main part of the talk here. There's going to be a few scenarios that I want to show you, think about, and then we'll actually implement to some extent in C# code, a couple of scenarios like that. Okay, so imagine you say, well, if I want to split up my data into chunks, let's say I have split up, instead of one database, I have 5 databases here, and I split up my data by customer number, 1 through 499 and so on and so forth. So it's like, about 500 or so per physical machine. And so I split that data up this way, and that's pretty cool. That sort of makes sense. But the problem is that maybe the last shard is not filled yet. You're anticipating the future and so on. So what I'm getting at is the data is not evenly distributed. That you picked a number and then you sort of, had these imaginary lines between your data. Remember, this is horizontal partitioning. So imagine all these records in your database for all these customers. You're slicing portions horizontally and saying, oh, that's one shard, this is one shard, and so on. It seemed to be some form of arbitrary way of doing it. So let's use it, most of our queries are based on username. And this is how you think about the shard. Like, what should the shard be on? Should it be on the customer number? Should it be on the username? Should it be on something else, right? Depending on the kinds of queries that you're finding, the shard should be decided based on that. The idea is that if you're querying, let's say, on customer, let's say username or customer ID, then that should be the shard, since most of your queries are based on that. But it's not that's how you do the partitioning there. You just, cut off from certain numbers because it's not evenly distributed. Let's go through this a bit of a mental exercise here. Let's imagine we've done it like this with all these customer numbers, the way we have them here. And over the period of a week or so, you looked at the number of requests that each of these machines had because of the way you've broken up this just arbitrarily by customer number. And you find that, let's say, this machine is the one that gets hammered the most. Or maybe these two are the ones that get hammered the most. These two are hardly even touched. And this one is sort of barely touched. And you might find that's because, newer customers, these are like the newer customers, these are the newest customers. And these are the really old customers. By old, I don't mean age. I mean just they've been your customers for a long time. They're the least active or something, right? Let's say that's happening. And so as a result, these servers are hardly ever being used. These are moderately being used, and this one's being used quite a bit more, except it's got hardly any data in here, so it's able to cope. The idea with the shard, or the way you do the sharding, is to have an even distribution of workloads. Right? You want all 5 machines here to be utilized exactly or equally, so that you're not having to beef up one machine. And then if this phenomenon grows over time, you'll find that the older customers, the machines that are housing the older customers are becoming less and less active, and then the newer customers are becoming more and more active. I'm just coming with a theory right here, but you understand the point. The same thing could happen for if you let's just then divide this by name. Like, you remember the old telephone books? Are you old enough to know what I'm talking about? These old telephone books had tabs on the side, and each tab was like a range of letters. I forget the range and how many tabs there were, but basically, depending on whose name you were looking up or entering, you flip to that tab and then add some record there, handwritten. Let's say we did something like that. In fact, YouTube did that in the beginning, or maybe they just talked about them as an option. But when YouTube first started, they had to think about some sort of strategy, and I think they went down this one route, and then they realized that was a bad idea, and they sharded it a different way. So let's say instead of this 1 to 149, this is A through something else, and so on. So every database server here is a range of certain letters. The same thing is going to happen again. It's arbitrary sharding, but the load is not representative of the sharding kind of grouping that we have. And so again, that's not a good idea, right? So to mitigate this sort of stuff, we know what you want to shard on. Let's say, customer name or customer ID, whatever it is. But the splitting up of the data is not correct in the way we are thinking about it. Right? So that's where the sharding or the hash functions or the hashing comes into play. So I'm switching into hashing. So what is hashing? Essentially, it's the ability to take a large chunk of data, small or large, makes no difference, and it sort of hashes it into a number of a certain size, bit size. By number, the bit size is the same. So if you have a hashing algorithm that's let's say 32-bit hashing algorithm, then it can digest that data, incoming data, into an output of a 32-bit number, right? And no matter how big or small the data input data is, its output is always the same size. Because these days you have 512-bit digest or hash functions, and so it'll produce, no matter whether you give it a single character as your input or the entire 10 gigabit document, it'll digest that to a fixed size of 512 bits. So that's the basic idea. It's kind of like a compression of sorts, but it's more like it's a signature. It's not, so don't think of compression, because it's not a two-way thing. See, compression means you can decompress. You can't go back. It's a one-way operation, right? But this document will always produce this digest or this signature or this hash code or this hash value. There's many names for the same thing. It's always going to do the same thing. And for the exact input, the output for the specific input, the output will always be the same. And based on the hash algorithm, the bitness, as in how many bits occupy the output, is also going to be the same no matter how big or small the input is. Right? So these are some features of hash functions. Some others are, they should be fast enough so they don't slow things down, but not too fast, because apparently there's a problem when hash functions are too fast. They also make hacking faster. So there's a compromise between how fast to make it so that it doesn't aid the hackers but deters the hackers. And there are the newer hashing functions are, in fact, you can control how slow to make it go. Like there's bcrypt and Exon2, I think. I forget, but bcrypt is one of them. And one of the arguments is, how slow do you want me to go? So too fast is not a good thing, even though we might think that's what we want. We want to make it just kind of right. Another thing about hashing functions is, let's say you take a document, and I'll show you this stuff happening. So I'm just talking now, but then we'll switch to C# code. You take a certain document and you get the hash for it. And let's say it looks in a certain way for you, right? And you make a small change. Maybe you added a space, maybe you added a comma, maybe you deleted one character or something, and you hash it. That hash looks completely different. So you would never be able to tell that this document and this document are like in any way connected, because there's just a minor change between this document and that document. The requirement for hash functions, that is the hash, completely changes. So there's no resemblance of one document from the next, even though the only difference is a small, tiny little thing that changed. You and I might not even know the difference. Like, would I see if a space was extra in a certain place, or the period went missing or something? Probably not. But the hash should look totally different. So that's the requirement. All right. So let's look at now in practice. What I have is I've extracted from my online telephone book, not the physical book, 5,000 of my friends whose names are unique. So there are some people they have the same name. But you don't have 5,000 unique friends? No? Have you seen my subscribers lately? No, I'm kidding. That's not my subscribers. I've just generated 5,000 unique names. They have nothing to do with my own telephone book or my subscriber base. So if there's any connection between your name and the names you see in this random list, it's just a fluke. But they're totally random names. But there's 5,000 of them that are all unique. We're going to use that as our sort of source. So let's look at that, and we'll go through the motion. Looking at the code, I'll explain the different steps I'm taking, and that way we can see how this all is going to work eventually. And we'll tie it all back to the sharding thing that we're basically talking about now. right? Okay, so I have this file here with my person names. As I said, there's each line is a name, and there's 5,000 of these names here. Oops, there. So that's 5,000, right? And I read those names in. Okay, right. I read those names in here. I'm reading all lines, so every line is really a person name. Okay, so now what I'm going to start with is, let's do this. Let's do, I'm going to use the MD5 function. Now, MD5 and SHA1 or SHA1 are no longer considered sort of good hashing functions. They'll do just fine for databases, by the way, but from a security standpoint, they're not the best because they have collisions, meaning there are more collisions. That's another feature of hash functions, by the way, that for every unique document, the hash output should be unique, right? So there should be no collision. I mean, no two different documents should produce the same hash. And that's not completely feasible, but the better these hash functions are at that, the fewer the collisions they have, the better they are considered. MD5 and SHA1 are not considered that good anymore. You know, they're older, but we don't care. We're not doing that from a cryptography standpoint. And we'll use the other ones too. So I'm just starting with MD5 here. So let's say I create they're typically called hash algorithms. So I'll just hash algorithm is equal to that, right? So that's the hash algorithm. And I take the hash algorithm and I compute the hash for this. Now, when I compute the hash, it requires a byte array of whatever it is that I'm trying to compute the hash for. So what I want to compute the hash for, one is the first person, right? But it needs a byte array. So I've got a string now. I need to get encoding.udf8.getBytes. All right, that's my byte array. Okay. And this in turn returns a byte array again. I need to then convert that byte array to a string. The byte array is really a byte of integers in the form of byte arrays. So I'm going to convert that to hexadecimal, just because that's kind of like what you normally see. It's rather than integers, I'm going to use hexadecimal. So I'll get this byte array here. Let's call it hash bytes. And we'll say get hash. Let's call it just get hash. I'll send it the hash bytes. All right, and we'll print this out to the console since that's supposed to return a string. Get hash. Let's call it get hash value. All right. So here we get the hash bytes. Now what I do over here, once I got the hash bytes, I need to iterate over each byte, and for each byte convert it into hexadecimal, add it to let's say a string builder, and then return that eventual thing out here. All right. So for each byte, I don't think I'll be able to do this byte. You can actually put the at symbol in case your collision with the name in hash bytes. This is called hash bytes. I'll just call it hash byte singular. Hash byte. Okay. So for each hash byte, I need to now convert that. So the byte itself, so hash byte, has a toString. The toString can say it needs to convert this to hexadecimal two positions. Right? If I did this as uppercase, then you'd see the letters appear as uppercase A through F, whereas lowercase will be lowercase a through F, but occupying two places. And this I need to add to a dictionary, string builder. All right. Once we do that over here, we can do sp.append. And we append that. And once we run through all of this, we can return the sp.toString as the string representation of this. Oh, I need to return this. Okay, so this should work. Let's see what this looks like. Okay, that's what the MD5 hash for the first name looks like. All right, let's do the same for not the first name, but the entire document, this whole document. Right, so I'll call this again. But this time, rather than the first person, I'll do a file.read all text from the same file. Right, so that should be returning. I'll get the bytes for that. So this is the entire file. And let's look at the difference between these two MD5s. Probably have to give it a different name here. Right. And they both they have the same size, of course. They both look completely different, but they have the same size. What I was trying to show you is no matter how big or small the input is, the digest or the signature or the hash value or the hash code, they're all the same, by the way, have the fixed size. All right. So now let's use another hashing algorithm rather than MD5. Let's say we use, SHA-1 just as an example. They're all descendants from the same thing, so they all return a hash algorithm. So it's very convenient to flip from one to the next. So it's become a little longer. The bitness is higher in SHA-1. So, but they are both the same size in terms of number of the width, if you will, number of bytes or bits. How about SHA-256? How about SHA-512? Okay, let's see that. So of course it's longer. It's gone that wide, but I don't think I can zoom this in. It might not fit into the screen. Yeah, it's too wide. Okay, never mind. Hopefully you can see that, but that's that big, right? But this is a number, and of course every number is hexadecimal form, which you will then eventually do something else with. So you got this part, and now, so if you got hashing, just generally the concept, and I know this, I'm harping on this because I know a lot of people I've worked with have had this sort of confusion. Okay, hash it. What do you mean you're going to hash it, right? So this is what we mean by hash. We use a function whose purpose is to digest the data and output a hash value, which is a number. In this case, we are displaying it as a hexadecimal number. So basically, it's letters from A through F and 0 through 9, number 0 through 9, right? And now what, right? So now let's go back to our sharding concept. Now that you understand hashing. All right. So we have this number range, and the idea of the hashing function is to not have any collisions. So let's say, for example, if you had, so let's say you have 1 million customers in your database and you want to hash their, let's say, username you're going by, or, username, you go by the username. And when you hash them, you're going to get 1 million different unique hash codes, hash values, or hash signatures. Let's assume that's the case. What do you do with these 1 million now? The aim is to distribute those 1 million across these 5 machines, physical machines, because we decided we want to scale out to 5 machines, right? So the hashing is not really helping us, but what hashing is doing is it's giving us this randomization of a name, right? So that randomization in turn is giving us the ability to have fewer collisions. And so now as we go to the next step, you'll understand what's happening. Once we have this number, we have to be able to fit that number. So these numbers can span all the possible numbers, in the form of, like, say, integers, right? So minus 2 billion to 2 billion plus 2 billion. All those numbers we're going to try and fit down or funnel into 5. Because we got 5 machines. We decided for 5 machines. So how do those numbers get into these 5 machines? Well, we take the modulo or the modulus of the number of 5. So we mod 5 it, which basically means we divide the number by 5 and we get the remainder. Now, if you divide something by 5 and the remainders will be from 0, that is nothing, to 4, right? So you'll get numbers from 0 through 4. And now that number tells us which machine to put the data in. So as we are sharding this database, we're using the hashing function to hash the key that we are attempting to partition by. And then we hash it. We mod, in this case, mod 5 it. The remainder is the machine number in which we put that data. Right, so we're going to go through this process very quickly and see that our aim is to look at the distribution. Right, so of course, there'll be some collisions. You can't take 4 billion numbers and shove them down into 5 machines and expect no collisions. But the distribution should be even. That's what we're looking at. Right? So let's look at that. I'm going to remove all this stuff now. And what I'm going to do is I've got the hashing algorithm, that's just fine. I do a for each on every person name from person names. Okay, for each name, we can get, hey, actually, you know what? This is seeing this here. In C#, every object has a get hash code. Why not just use that? What do you think? Okay, let's do it. Okay, well, luckily I haven't gone too far here. So this person name should have a get hash code, right? This is an object. Every object has a get hash code. What do you do with this hash code? Now, I do have a data structure that I'm going to explain in a bit. I'm just going to call it tables dictionary, but it is of a type one-to-many dictionary. Type string. I'll explain all this so you don't get confused. All right, so the one-to-many dictionary is essentially like a dictionary, but the key is 1 and the value is many. It's a hash set on the value side, and hash sets don't allow duplicates. If you haven't used a hash set, then it is a super fast set-based data structure. It's got more features than like links. Link has like things like intersect and accept. This has not only intersect and accept, it is a proper subset, proper superset, bunch of other set-based operations. But one of the unique features of it, like any other dictionary, is it's only a single value, right? It's not like a dictionary. It's a hash set that has just a single value, and it only allows uniqueness. So the idea is that for every machine ID, right, that hash code will give us the machine ID. We will put the name of the person in this hash set. So it's a one-to-many per machine, and number of names are going to go in there, right? We get the hash code. So here's the hash code. Now what would you do with hash code? We need to take the hash code and we need to mod it by, I said 5 in this case, right? So we take the hash code, we mod this by 5. Now, because the hash codes can be minus numbers as well, we do them the math.abs absolute. So we get the absolute for that. Let's do that. Math.absolute value. That'll give us a positive number. And that should result in our machine ID. The machine into which this name should go. And then the name. Right? So if you did that, what I could do is I could take this tables dictionary and now add it. I could say add this machine ID and the name, the person name. Right? Okay. I don't like this ID. It should be lowercase. Okay. Oops, I should have done it. Oh, this needs to be a string, which is correct. Plus, we need to print out the result of this. So again, iterate over all the collection. Oops, and do a for loop. And this would be for every machine in tables dictionary. So this table dictionary will give us a numerator. This is actually a key value pair, right? It's a key value pair. So the key is that and the value. So we want the count, the name of the machine, the number of the machine, and then the count. So here we'll type in the machine and the number. So that's machine.key, right? And let's say the count. And the count will be machine.key, but this time on the main dictionary, we need to get the actual thing dot count. And count is a get. All it is, right? Okay, that should do it. All right, let's try that. Okay, so this is, hang on, let's just sort that. What is this? Was it this that is not sorted? This is not sorted. Okay. Order by the key. kvp.key, right? And that. Okay. Now let's try it. All right. So the machines from 0 through 4 have, in this case, counts of so many people's names. In this case, 997 in machine 0, 1025 in machine 1. This is a fairly good, even distribution, actually. It's not bad at all. Fairly even. But one of the other criteria for hash functions is that the same input should always result in the same output, the same hash or the same signature, right? It's not okay to change the signature. So let's see if that's true of our get hash code. Let's look at machine 0. We have 997 and machine 2. Remember the numbers, right? 997, 1025, 1026. All right. 997, 1025, 1026. Whoops. Totally changed. What if we did it again? Changed again. So every time we run it, it changes. Of course, it's not going to work. So there must be something wrong with the get hash code function, right? No, nothing wrong with the get hash code function. In fact, it's a pretty decent get hash code function. So then what's going on? Why are those things changing? We're using the same name all the time. Why is it that for the same name, the hash codes are differing such that the distribution is changing? Do you get it? Okay, for those who didn't. The hash code is not coming off of the name. The get hash code is coming off of the object reference. And the object reference, of course, is changing. Each time you run your application, it's a completely different object reference. And the hash code is based on the object reference, not on the actual data value. The hash code function is doing its part, except we're using it incorrectly. Okay, so let's do the real thing now. Okay, so instead of using the get hash code thing here, we'll use our hash algorithm, right? So our hashing algorithms dot compute, we'll get the compute hash, and we'll do the same thing, encoding and encoding .utf8. Sorry, I have difficulty reading the screen with all these bright lights. Don't get bytes, and I want the bytes of the person name. Not. Okay, that's my bytes. The bytes have to be converted to an int. This is my hash bytes. Convert this to ints. Okay, don't need that. So then we do bit converter that convert to int32 these bytes, the hash bytes. Okay, and that gives us an integer, and this will then be given to our that. And that'll so on. So it should all work out. Now let's see how this turns out. All right. All right. So now we have Now we have to remember these numbers just, for starters, 1020, 1007, 958, 994. Let's run it again. 1007, 958, 994. Let's run it again. 1007, 958, 994. So this is very good. The distribution is really good. And so is the consistency, right? Which is expected. Of course, these things are coming from the cryptography libraries in .NET, so they're not playing around here. These are pretty solid hashing functions. So what we've done is we've taken our data. Now let's see, we have to confirm that the data is correct as well, right? So the other option is, if you haven't thought about this, is the other requirement is we have to be able to find this thing. So now that we distribute all this data in these different machines, what do we do when we have to retrieve them or query, right? Right. So imagine your application, you take the incoming name, you hash it, you go through the same process. From that hash, you get to the machine ID. And now you know which machine to go to and get the data from, right? So maybe it's a connection string that you have, for the different machines, and you determine which connection string should be used. Therefore, what, database engine you're going to connect to and query for that specific requirement, for that specific request. So you have to be able to use, because the hash functions are for the given input, it has to produce the same output. We should be able to use that to now, for every person in the system, we should be able to find the thing in the right person in the right machine. So let's test that out too as well, right? What I'm saying is, now that we have the data in here, given the set of original names, we should be able to find the person in one of these tables, and we would know exactly which table to go look for, or look in, right? So let's do that as well. So here we're going to, this time, do the loop around the person name again. And this will be from the person names collection, the original person names. And so that's the ones we read out of the file itself. We're just going to iterate over that collection again. But this time, for every person, we'll hash it and do all the stuff, right? So we'll, person name, we'll get the hash, we'll do this, we'll get that. Now that we have a machine ID over here, right? We can query our dictionary. We say, hey, for in this dictionary, using that machine ID, right? So we use this machine ID. Now we get the sort of the hash thing. We want to see if it contains the person name, right? We want to contain, if it contains this person name. And if it does, that's great. If it doesn't, then that's a problem, right? So let's see that. And this, of course, needs to be a string. So get that to a string. If you run through this and there are no errors, it effectively found for every person. It found that person in the actual machine we're expecting based on the hash function that we have here. All right, let's run that. If you don't see any errors, we just see the output from here. We're good. Well, there you are. It came here with no errors. We're good, right? So hopefully this explained to you not only hashing and hash functions and how to use them and why they use, but also database sharding or horizontal partitioning of a database if you're looking at scaling out your database using sharding, which is probably the more common feature. Of course, the read replicas are as common because that's one of the first issues you have is the load on reading your data, query, reports, that sort of thing. But sharding is a very viable option for databases, horizontal scaling of databases for normal OLTP workloads, not warehousing and not reporting workloads, but OLTP workloads, right? So, all right. So this brings us to the end of this video. I hope you enjoyed yourselves. I hope you learned a few things. If you have, please give me a thumbs up and I shall see you next time.